Okay, in this video I'm going to talk about the cyclic quadrilateral formed by segments at equal angles from the opposite sides of another cyclic quadrilateral. So basically we have an arbitrary cyclic quadrilateral. Cyclic, it means that it's inscribed in a circle. So there exists a circle that passes through all four sides, all four vertices of this quadrilateral. So let's say something like this. Yeah. Something like this. And we take two opposite sides. So let's say we take these two opposite sides, and then we take the segments at equal angles from these two opposite sides. So like this and like this. So these two angles must be equal. So from these two vertices, we take segments at we take lines at equal angles from the opposite sides, and the intersection point with this side, we take the segments. So now basically this quadrilateral is cyclic. So like in this case, it looks kind of like these lines looks kind of parallel, so I want to avoid this. So let's say slightly more like this. Yeah, like this, so that these angles are equal to each other. And then this quadrilateral is also cyclic. So basically, if we denote the points, EF, so basically the theorem is that so ABCD is cyclic, and then the angle ABE is equal to the angle DCF, then it implies that BCFE is also cyclic. Cyclic, it means that there is a circle that passes through all these four vertices. So a circle like this. Yeah, so that's the theorem. So let's now prove it. So basically, one of the criterion of a cyclic quadrilateral is that the opposite angles must be 180 degrees. So quadrilateral is cyclic if and only if the opposite angles, the sum of the opposite angles is 180 degrees. Or another criterion is that, so let's write this. It's kind of well-known fact. So if the sum of these two opposite angles is 180 degrees, or another form of this criterion, if the angle is equal to the external opposite angle. So if this angle is equal to this angle, then even though leave this quadrilateral is cyclic. So we are going to apply this in both cases for the original cyclic quadrilateral and to prove that the new quadrilateral is cyclic. So let's denote this angle alpha and this angle x. So then this angle is also x by the condition. And the angle C, so the angle BCD is equal to 180 degrees minus alpha. This is because the ABCD is cyclic, right? So like we can write ABCD is cyclic implies that the angle BCD can be expressed as 180 minus alpha. Therefore, the angle BCF is 180 degrees minus alpha and minus x, because, well, we can write it more in a more detailed manner. So it's equal to the angle BCD minus the angle DCF. So BCD is equal to 180 degrees minus alpha, and DCF is equal to x. So we have 180 degrees minus alpha minus x. Okay, and now we need to calculate the angle BEF, this angle. So let's remove. So we just calculated DCF, not DCF, but BCF. So we calculated BCF, so it's this angle. And now we're calculating the opposite angle in the quadrilateral that we need to prove that it is cyclic. So it's this angle, right? So BEF, so it's an external angle in the triangle ABE, right? In the triangle ABE with the angles alpha and x. So it's equal to the angle BAE plus the angle ABE. So which is equal alpha plus x, right? External angle in this triangle. So in total, the sum of the two opposite angles in the quadrilateral that we need to prove is cyclic is, so BCF plus the angle BEF, it's equal to 180 degrees minus alpha minus x plus alpha plus x. And this, of course, is equal to 180 degrees. Which immediately implies that the quadrilateral BCFE is cyclic, because the sum of the opposite angles in this quadrilateral is equal to 180 degrees. So this concludes the proof.